Imagine you're building a recommendation system for a massive e-commerce platform. You want it to understand not just what users like, but how they're connected, what products are frequently bought together, which users influence others, and how communities form around brands. This is where graph data comes in, a powerful representation of relationships. But here's the catch. While graph neural networks, or GNNs, are the gold standard for analyzing such data, they come with a major downside: high computational cost. Their message-passing mechanism, which aggregates information from neighbors across the graph, is incredibly expressive, but also slow and memory-heavy. This makes them impractical for real-time systems, like mobile apps or live recommendation engines, where every millisecond counts. So what if we could capture the intelligence of a GNN without paying the performance price? Enter InfGraND, an innovative framework that distills knowledge from a powerful GNN teacher into a lightweight multi-layer perceptron, or MLP student, while preserving performance, eliminating inference overhead, and doing it all in a way that's structurally aware. Let's break this down. MLPs are fast. They process node features directly, skipping all the complex graph operations. But because they ignore the graph structure, they often underperform. Training them on labels alone gives poor results, especially on real-world graphs where community patterns matter. One promising solution: knowledge distillation. Here, a well-trained GNN teacher shares its wisdom with an MLP student by teaching it to mimic the teacher's soft predictions, its confidence across classes, not just the final labels. But most distillation methods treat every node the same, whether it's a central hub in a social network or a random outlier. That's like teaching a student by giving equal weight to every example in a textbook, regardless of how important each chapter is. We asked, what if we could prioritize the most structurally influential nodes during distillation? InfGraND introduces a graph-aware influence metric, a way to measure how much a single node affects the representations of others after message passing. Think of it like this: if you remove a key influencer from a social network, how much does the overall structure change? Nodes with high influence are those whose features, when perturbed, ripple through the graph and alter the embeddings of many other nodes. To compute this, we use a clever approximation. We simulate a simplified version of a GCN, removing nonlinearities and weight matrices so that the model becomes purely topological. Then, we calculate the cosine similarity between the original node features and their two-hop propagated embeddings. This gives us a parameter-free, efficient estimate of influence. We normalize this score across all nodes to get a global influence score, a value between 0 and 1 that tells us how central each node is to the graph structure. And here's the key insight: high-influence nodes are the most critical for generalization. We tested this by training GNNs only on high-influence versus low-influence nodes. The results were clear. Models trained on high-influence nodes consistently outperformed those trained on low-influence ones, across Cora, Sightseer, PubMed, and more. This proves that structural importance drives performance. InfGraND combines two powerful ideas. First, influence-guided knowledge distillation. During training, the student MLP doesn't learn from all neighbors equally. Instead, the distillation loss weights each neighbor's contribution based on its influence score. The loss function looks like this. For each node, we encourage its prediction to match the teacher's predictions on its neighbors, but the stronger the neighbor's influence, the more weight it gets. Mathematically, we add a term: gamma 1 plus gamma 2 times the global influence score of neighbor V sub j. So if a neighbor is highly influential, say, a central user in a recommendation graph, the student learns from it more strongly. If it's a peripheral node, it contributes less. This creates a fine-grained, structure-aware learning signal. And to ensure we don't lose signal from less influential nodes entirely, we keep a baseline term, gamma 1, so the student still learns from all neighbors, just with a bias toward the most important ones. Second, precomputed structural features, no inference cost. The second innovation: enriching the student's input with multi-hop neighborhood information, once offline. Instead of doing expensive feature propagation at inference time, we perform a one-time pre-computation step. We run a linear propagation, like SGC, over the graph for a few hops, say 2 hops, and average the resulting embeddings. Then we pool them, no concatenation, no explosion in dimensionality, into a compact fixed feature matrix. This becomes the student's input. No extra computation during inference. No latency. But the MLP now sees rich structural context, like knowing not just what a user likes but who their friends are and what those friends like. This is inspired by real-world industrial systems, like embedding tables in large-scale recommendation engines, where precomputed features are stored and retrieved efficiently. We tested InfGraND on 7 real-world graph benchmarks, including Cora, Sightseer, PubMed, Amazon Phode, co-author co-author and the massive OGBN-Arxiv dataset. We used GCN, GAT, and GraphSage as teachers, and compared against state-of-the-art distillation methods like GLNN, KRD, HGMD, and FFGTWM. The results: InfGraND consistently wins. In transductive settings, it outperforms vanilla MLPs by an average of 12.6%. In inductive settings, it beats them by 9.3%. Most strikingly, in many cases, the distilled MLP surpasses its own GNN teacher, a rare result that challenges the assumption that GNNs are always superior. Even on OGBN-Arxiv, where the graph has over 169,000 nodes, InfGraND outperforms KRD by 0.4% on average, while being 8 to 14 times faster than the GNNs it replaces. And when labels are scarce, say, only 2 nodes per class, InfGraND still outperforms GLNN by 4.17% on average, thanks to its ability to focus on the most informative nodes. This isn't just academic. In production systems, whether it's fraud detection, personalized recommendations, or graph-augmented LLMs, latency and efficiency are everything. InfGraND delivers high accuracy, matching or beating GNNs. Zero inference overhead, because influence scores are computed once and features are pre-processed. Robustness, even with few labels. Scalability, from small graphs to millions of nodes. And it's built on a principled, interpretable signal, not prediction uncertainty, but structural influence. InfGraND redefines what's possible in GNN to MLP distillation. It moves beyond uniform treatment of nodes and introduces a graph-aware, influence-driven learning process, one that's both smarter and more efficient. It shows that you don't need complex models to learn from graphs, you just need to learn from the right ones. This work opens new doors, from deploying efficient graph-aware models in edge devices, to integrating structural knowledge into LLMs via retrieval-augmented generation, to building hybrid systems that combine entropy-based and structure-aware sampling. The future of graph learning isn't just about bigger models, it's about smarter distillation. And InfGraND is a major step in that direction. If you're working with graphs, building recommendation systems, or pushing the limits of efficient AI, this is a framework you should know. Stay curious. Keep learning. And remember, sometimes the most powerful insights come not from the most complex models, but from asking the right question. How important is this node to the structure of the graph?